All right. So hello, everybody. Let's start the lecture number 6, I believe. So we had a 1 week of break. It feels like it was a month for me. I almost forgot what we were talking about last time, but if I remember correctly, we ended up on okay, so we made a couple of conclusions at the end of the last lecture. So one was that the classical theories that we are familiar with are trajectory theories. So those that can be reformulated essentially as a theories of stochastic processes. And we checked that the theory we are analyzing right now is not one of those, okay? Because measurement probabilities are inconsistent, right? That was observation number 2. I think I can find it somewhere. Right, it's this observation number 2 that measurements are inconsistent, therefore it cannot be one of those classical theories. So this is kind of right. Where to go next from this point, right? Because like if it's not like all the other theories, then we should try to like figure out what is it. Like if it's not a trajectory theory, then what kind of theory it actually is. And it's you have to like kind of intuit what kind of measurements we have to do next, right? To like tease out some answer to this fundamental question. What are we dealing with? And so to like kind of guide us where we want to go next, it's good to like take a look at those theories we are familiar with, so trajectory theories, and like examine their like fundamental properties, especially those that are concerning the measurements, right? Because we are dealing with measurements here, we're describing sequential measurements. So what classical theories tell us about those kind of experiments, and maybe we can like, figure out some clever test that would expose some weirdness about the theory we are looking at right now. So last time we discussed the idea of fundamental or essential invasiveness of measurement and non-invasiveness in the classical theories. That could be like one of the clues where to go next. But on this our previous discussion, I criticized this concept, and so the conclusion is that this is a dead-end kind of pursuit. The invasiveness, non-invasiveness of measurements is not the thing that will give us anything concrete to work with. But there is another thing about measurements in classical theories that will actually lead us somewhere. And this thing I want to talk about right now, I already teased it a bit at the end of the last lecture, but there is this very peculiar thing that in classical theories that is trajectory theories. There is only one observable. Okay, so what does it mean? So to explain what this means, it's like, so if we are dealing with classical theory, they are classical because we can assume that whatever kind of measurement you are doing, whatever kind of measuring devices you are applying to your system, the probabilities that you will obtain as a result are have to be consistent, right? So that the trajectory picture can exist. So if we assume in classical theories, we assume all measurements are consistent. That is, if you take the probability, multi-time probability distribution, where we are measuring some collection of classical, how to write it, maybe CLS, superscript CLS to denote that we are dealing with classical observables. So we assume that we have a consistency relation always satisfied. Classical. Okay, and this implies that there exists for every observable, then there have to exist a master probability measure for its trajectories. Okay, so in other words, if it's always consistent, then there is always a trajectory for the master measure on the space of trajectories exists for every observable. So in other words, the trajectories of each and every observable just unravels in time simultaneously. So in other words, at every point in time, the value of every observable is always determined, okay? Simultaneously for every possible observable. And thus you can take, if you take all this set of all possible observables represented by trajectories, and you can pick from this set only those trajectories that are mutually independent of each other, okay, and treat them as components of one big vector observable, okay. So you could imagine that you have something like this, some E1, T, E2, T, okay, where all these guys and so on, EJ are independent of each other. And then you would have probability, master probability distribution on space of those vector trajectories, okay? And we would call them this like elementary observable. So if E contains all the components of E are all the independent trajectories, right? So then any other observable would be some function of those components, right? So in this sense, every observable can be expressed as in terms of this elementary observable, right? So this is what I mean when I say that there is only one observable in trajectory theories, okay? So you can think maybe some simple system like a material point, this elementary observable will be probably position or three components of position X, Y, Z, right? For some electrodynamical system, you would probably have three components of electric field, three components of magnetic field, and some density of charge, right? And the number of independent of components of this elementary observable would be probably I think you would call it a number of degrees of freedom of your theory, I guess. So if this is the case, if every observable can be expressed as a function of this elementary observable, this has a certain consequences for those sequential measurements in classical theories. So if some arbitrary observable X classical is a function, function of E, the elementary observable, the LM observable, then the probability so this joint probability, multi-time probability distribution would have to have the following form. That you have a product Jn, and here you have some filter function, classical, could depend on time, xj, given the value of elementary observable at time tj, and all this integrated over trajectories of the elementary observable. So if xj is a function of E, right, then the value of x at time tj depends in some way, some form, depends on the value of E at that time, right? Then you can express it as a through filter function or like this conditional probability, however you want to call it. So and this you can rewrite it in terms of joint probability distribution for this elementary observable E. It's also classical. That's right, classical. Classical Tn En and times our filters. Xj, classical J, Xj, Ej. Okay. So this is a consequence of having this trajectory picture in your theory. There is trajectory picture. The measurements have to be consistent. Then, if they are, then you can pick this minimal set of independent trajectories which form this vector elementary observable, and every other observable is then a function of this elementary observable. Therefore, all measurements have to be of this form. Okay. And now, so this all comes from consistency of of measurements, right? So now we are dealing with a theory that is inconsistent, right? So the measurements don't violate in general the consistency condition. Therefore, we don't have this constraint on trajectories that they have to be, the value of every observable have to be determined at each point in time, which leads us to this reasoning that gives us the idea of elementary observable. If there is no consistency, there is no reason to have this kind of elementary observable at all, right? So it's quite possible, and it's most likely that in this quantum theory we are investigating right now, there are many non-equivalent observables, okay, which is kind of, you know, it's difficult to wrap your head around this concept, because we are used to thinking about measurements, observables, dynamics, and stuff like that. Our intuitions are all based on, you know, our experience with classical theories, right? Theories with trajectory picture, valid trajectory picture. Therefore, our conceptual basis is a universe where there is, you know, every system has only one elementary observable. You can explain everything through those in terms of this elementary observable, right? And now we are facing a situation where there might be more than one, and there is no way to like interpolate our intuitions from, you know, single observable to more than one. It's just, you don't know how to think about it too much, right? It's just you know, a new concept, quintessentially non-classical concept, right? And probably, and this is like the way forward to like tease out what is the structure of this quantum theory we are investigating right now would be something that deals with you know, those different inequivalent observables. You have to like see what it implies, okay? But again, you know, just having a knowledge that there might be more than one observable, it's still, you know, difficult to wrap your head around it. But there is an idea where we can think about. I mean, okay, there is an entry point here, okay, which we'll talk about right now. Is this? I don't have reactions in the audience too much, so you know, if there are some questions, please you know, let me know. If it's unclear, let me know, right? Because I hope this was kind of clear what I was trying to say here. All right, so okay, so the basic idea now is to like figure out. Okay, let's try to do some experiments where there are different observables involved, right? Non-equivalent observables. But we don't want to go too hard on that, because you know, we are on the uncharted territory right now. So do we have an idea about some kind of like observable that it's not exactly, so if we start with some F device, right? So we have some device, it measures some observable, right? And can we figure out some, let's say, different observable that is somehow in understandable way related to this F device? And the thing that comes to my mind is, okay, so imagine you have, so you have this device, but you bring in another device that measures the same observable, but with lower resolution, okay, with less definition. So in other words, you want to have a device that measures the same observable, but it coarse grains over it, okay? So we have F device, and we want to think about F bar device. So this would be a coarse-grained version of F device. So what do we mean by coarse-grained measurement? So like in pictures, right? So where my intuition comes from. So imagine that, you know, if F device F would be something that you know, if we have just bunch of values the device can resolve. Let's say F prime, that would be F prime, F B's, F threes, and so on, right? So F bar, I would imagine that it like takes when it does its measurements, it's kind of clumps together certain fine grain results. Okay, so that would be F prime, F bar prime, that would be F prime B's, and so on. Okay, so if at some point we apply F device to measure it, and it displays one of those, it would display one of those results. So all things being equal, if you deploy the F bar device, it would always display only this result corresponding to this whole, you know, blob of device of results of finer measurement. Is this picture clear?
Oh yeah.
Yeah, it's kind of intuitive, right? What's going on here? So this I will to make it possible to talk about this stuff. Let me introduce some notation. So this this will be you know, fine-grained measurements, and this this bracket, okay, I will call those brackets omega, small omega of small omega as a function of the result displayed by coarse-grained device. And so for example, so omega primes, so this guy, that would be a set composed of F prime, FBs, F3s, okay? Because those are the fine measurements, fine alternatives, which are like blobbed together by F bar device, okay? So having this, like formally describe the relationship between a coarse-grained device and its fine-grained version. You can I will define a thing that I will call resolution. Resolution will be res of F bar in respect to F, okay? And this will be a set. It's kind of mathy formal language, but you know, it's much easier to say what you mean. So it will be set of those omega sets. All right, which are subsets of the spectrum of device F. So just to remind you, this symbolized all possible results device F can display, okay? So we are partitioning this, all possible results of fine measurement, we're partitioning into groups, right? Such that F bar is one of the results that device F bar can display, okay, of course. The next thing we want is that omega F intersected with some omega F bar prime is empty set. So those omegas, like in this picture, they never overlap, okay? And when you take a union over all F bars of omega F bars, you get whole omega F, right? So this tells us that we partition the possible results of fine measurement into groups. Those groups don't overlap, okay, and they span the whole set. Okay, so this will be a resolution of a coarse-grained device. You could, of course, try to imagine a more complicated scenario where those measurements, they overlap a bit. Maybe there is some, measuring something from the center of the group is more likely than measuring something from the edges. We don't want to and don't need to introduce the complications. Just stick with this, the simplest scenario where you just the fine measurement device gives you a bunch of alternatives. Your coarse-grained measurement cannot distinguish between certain groups of those results.
So do I understand properly that this resolution is a set of omegas, yes?
Yes, so set of sets.
Right. Okay. And every set has possible outcomes that are bunched together as this one coarse-grain result.
Yes, exactly.
Right. Okay.
And they don't overlap. Okay, so it's much simpler to analyze. Okay, so sorry, I hung up because I looked at my notes and I forgot it's not the same page as was before. Okay. So this is like so we're trying to introduce the idea, and it will turn out that this concept of coarse-grained devices will be extremely useful. Okay, further down the line, and to make this to make the analysis using those devices more transparent, I will introduce a shorthand notation, okay, for dealing with them, because this resolution would characterize our coarse-grained device, right? And we will be looking at some measurements, so just some probability of getting those F bar results, right? Then you would have to look up this resolution, check what is this small omega corresponding to a given result, and stuff like that. Would be very annoying, very fast, right? So the idea is to introduce a notation that would give you all the information about those small omegas in line, essentially, okay? So we'll be using the following notation. Shorthand notation. So let us take a tuple of those coarse-grained measurements, right? So that will be some argument that we supply to our probability distributions, right, at some point. So to remind you, because we haven't used this notation, this particular notation for some time, a couple of weeks. So this thing means that this is a Cartesian product of omegas, right? N-1, and so on. Okay, shorthand for Cartesian product of all those guys. Right, so and this tuple is of course, right, it's something like this, and each result, right, would correspond to some small omega. So rather than like checking the definition, the resolution every time, I want to use like this symbol V. So it's like for alternative, to basically write down the whole contents of omega in line. So if we take let's say omega Fn to be some set composed of fine-grained results, FBs. Okay. I will write here. I will write it like this: Fn prime V Fn Bs V blah, 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 V and K. Okay. So I'm basically encoding the all information about omega in line, and you can use it for every other guy. V F Kn F1 some K1. Okay. To make it even shorter, I will also use big V notation. So Vn over Fn. Okay. So this, sometimes I will write like this. F1, right? Or even shorter notation, omega V n bar tuple V n tuple. Okay. Is this clear what's going on here? Hopefully it is. So that would be our notation we want to use. All right. So this is our idea what what the coarse graining device would do, right? But we are dealing here with some non-classical theory, so we don't know what to expect exactly. So we want to like take this idea and based on it, like define some criterion, like a phenomenological criterion that would allow us to to check whether some device that we are handed is actually implements this idea of coarse graining. Okay, so we have to define some condition that can be checked on phenomenological level to confirm or to deny that a given device is actually a coarse-grained version of some other device, right? So the one condition. So let me write here separator. Okay. Maybe let me change color a bit. So I will call it a necessary condition for F bar to be a coarse-grained version of F. It's a coarse-grained version in the sense that you can attribute to F bar resolution, right? This kind of resolution, okay? If you can attribute this, then that's the first step of having something that's realizes our idea of coarse-grained measurement. So this necessary condition would be we can use to like marry our idea of coarse-graining from classical physics with this non-classical situation we're dealing with. So we can somehow invoke the classical-like causality, right? That we learned about as our first observation, right? Because we know that you take the probability distribution for sequential measurements, you marginalize some over results in some mid-sequence, right? It's not consistent. But if you marginalize over the last argument, you get this kind of pseudo consistency, right? It's sum over the last, and it reduces to shorter sequence, but only for the last argument. And also, this also implies that like single time probabilities, right? If you marginalize over its argument, single time probability has only one argument, you sum over it, it has to reduce to identity because it's a probability, it has to be normalized, right? So we can kind of use this as our link with classical theories. Okay, we have here non-classical situation, but there is a bridge, let's say, at least it looks like a bridge with something we know from bridge between non-classical and something we know from classical. So necessary condition will look in the following way, that you take probabilities, single time probabilities, where you measure with fine-grained device F, right? You get some result F, and now you sum over F's belonging to omega F bar, okay? And we want it to be equal to a single time probability where you deploy a coarse-grained device, the candidate for coarse-grained device F bar that displays the results F bar. And it must be for all F bar belonging to its domain for all t greater than 0. Okay. So right, this makes sense, I think, but this is only necessary condition, not sufficient. Why it's not sufficient? Well, to understand why it's not sufficient, so why it is not sufficient. To understand why, we have to go back for a second to classical theories again. Where am I? So okay, I'm here. Good. Because the idea of coarse-grained measurement is clearly, we know what it means in classical theories, right? We are trying to model it on our understanding from classical theories. But but we learned previously like that there is only one elementary observable in classical theories. So coarse-grained measurement has to be it cannot be this elementary observable for sure. So coarse-grained observable would have to be some function of fine-grained observable for sure, right? So let's denote F tilde, maybe classical, coarse-grained coarse-grained obs in classical theory. So to implement our idea of coarse-grained measurement in classical theory, this just amounts to choosing a proper this proper filter function P, small p. Right? If you choose this P here properly, you will recover something that can be assigned this kind of resolution and will satisfy this condition, right? So constructing F bar class amounts to choosing a proper filter function P F classical T F bar F. Okay. So, and to get something that would satisfy this condition and also and automatically would allow us to assign the resolution in our sense to our observable. This is kind of easy. It's easy to see that you would have to set F classical F bar F to be equal to sum over some F prime belonging to omega F bar, right? So this F bar, he just put delta, Kronecker delta F, so this F prime. Okay. And when you do that, you put those filters in and you write down the joint probability distribution. It would be given by the sum over F PF classical EN FN. Okay, and here you put here all the filters 1 to n, F classical TJ FJ bar FJ given FJ, and it would just simply be sum over F when you put in all the deltas and do the sums. PF classical. In other words, classically speaking, the probability of getting a coarse-grained result is equal to sum of probabilities of getting the alternatives the device is coarse-graining over. Okay. So this is like, right, classically it makes sense, right? So it looks like the fundamentally you are actually measuring it looks like if you actually measuring like the fine-grained observable, right? And then just there is some post-processing after that, just the device just displays something that's smeared over, right? according to with accordance to its resolution. And classically, because of this constraint that there is only one observable, everything has to be a function of this elementary observable, and so on and so forth. This kind of f tilde is not only gives you a observable that satisfies this condition, right? But it's also within domain of classical theories is also the only way to achieve this, right? So this classically, this is the only way you can implement coarse-grained, right? However, if you don't have if you go to non-classical theory, right? I mean, in our scenario, we can implement this kind of classical like coarse graining. So we can we can implement f tilde in our non-classical case. Okay. I even already said how to do it. So to implement this for let me, because this is like fake coarse graining, I want to say. So I will call it for coarse-grained coarse-grained observable. For is like for leather, the fake leather. So it's like for coarse-grained, fake coarse-graining. Because in our non-classical theory, to implement it, it would be very easy. You just you deploy fine-grained F devices. Okay, you take this probability. I mean, you get your results distributed according to the joint probability PF, and you then let your devices to post-process the result. They basically measure, fundamentally, physically, they measure observable F, the fine-grained one, and they then just display to you something else, okay? So this post-processing, of course, is implemented by this kind of filter function as well. So if you choose the post-processing in this form, then your non-classical F tilde would give you the same relation as this classical coarse-grained, right? So you can so quantum F bar or non-classical F bar F tilde, sorry, would be how to call it, how to write it to be clear. Measure with F device first to obtain PF TFN, okay, and then post-process the results and display display to experimenter filtered outcomes. So you would take sum fn pf dn fn and the filtering, right? Some filtering. And if you set it as deltas, so you set it as omega fj bar delta prime of j, right? You will get fn belonging to this pf. Right? So it's easy to implement this kind of classical like coarse graining in our non-classical theory. It's just, you do fundamentally, you measure the fine grain and then you just cheat on the display of the device. That's easy to implement. However, because we are dealing with non-trajectory theory, right? There is no okay, it is possible to get a proper coarse-grained device F bar such that it doesn't have to be described by this kind of probability distribution. Okay. In classical theories, because there is only one observables in those, this form is the only thing we can do, right? But in inconsistent theories, like this theory we are investigating right now with quantum mechanics, you are not constrained by this, right? So, in other words, we want to have a coarse-grained device that, on the one hand, satisfies this condition, okay, but on the other hand, cannot be described with probability distribution of this form, okay? And in principle, it is possible to get such a device, or to put it differently, it is not forbidden in principle to create such a device, okay? Because we are not constrained by trajectory picture, this option starts to exist, okay, at this point. So a proper coarse-grained quantum coarse-grained device is a device F bar that on one hand satisfies this, and the other hand, it cannot be written, its probability cannot be expressed in this form. So physically, it would mean that this device, whatever it does, the way it measures, it has to rely on the physical process that is distinct from the process of measurement device F uses, okay? Because if this process was equivalent, then in reality, you would be measuring F without bar, and then would be some post-processing on top of that, which would be a faux coarse-graining, not a real coarse-graining. So this F bar device has to use some physical process that is different from the one used by F. So to like illustrate this idea maybe in more tangible way. So imagine, okay, we will cheat a bit and break our role play. And let's say that a measuring device is kind of the FF device is something like famous Stern-Gerlach like device, right? So it's like it operates by so we have our system, and then it's the device first like analyzes this system into a bunch of components. So, for example, you have a stream of particles with spins, right? And you have a gradient of magnetic field, which splits those spins into like spatially, components that are spatially dislocated, right? So imagine you have a input. So you have a beam here, right? Then you have some gradient that splits the beam into components, right? Then the device localizes those particular those components and can resolve them. For example, by scattering a light with short enough wavelength. Okay, and this is how it detects what is the value of depending on where it detects the components, where the scattering occurs, it assigns one of the values f. Right, so this would be some f prime. Okay, if the detection occurs like that, and afterwards you reverse the analysis step, you recombine all the components and send them further as a one beam again by, for example, applying the inverse gradient of magnetic field. Okay, so to get a coarse-grained device in this kind of model, well, what would you have to do? You would have to just make the light that's responsible for detection the wavelength, make it longer wavelength. Okay, if it is longer wavelength, it will scatter equally from the whole bunch of those dislocated trajectories. Okay, so it is a distinct physical process indeed, right? Because you're changing the wavelength of light. The scattering is different now. So it should be possible in principle, at least, to realize this kind of coarse-grained, real quantum coarse-grained device, not a fake coarse-graining a la classical measurements. And now, if we agree with this, we are able to find this kind of F-bar device that satisfies those conditions of ours. We can now experiment with this, okay? Which leads us to our next phenomenological observation. So when we will make a break, okay, after this. Logical obs, it's number 3. It's number 3. Let's call it quantum coarse-grained measurement. For our coarse-grained measurement. And it says, not let. When a proper quantum coarse-grained CG, okay? CGFJ bar device characterized by a resolution in res fj bar given fj. So fj would be the fine-grained device that we are coarse-graining over here, is deployed mid-sequence of measurements at time tj earlier than the last time tm. We observe that this would be another inequality, like in observation 2. So we have our sequence of measurements, we deploy fj bar mid-sequence, tm, j, t1. So we have fine grain measurement, and here we have of our notation, okay, j bar. And minus a version where we simply marginalize, not marginalize, partially marginalize over results of fully fine-grained measurements. This is every measurement was fine-grained here. Okay, this thing here is not equal to 0. That is, which means that is the readout of a coarse-grained device is not equivalent to the alternative of fine-grained readouts. So the coarse-grained measurement is equivalent to alternative of fine-grained measurements in classical theories. Okay, this is the only way to achieve this. So here we check that this is not the case in our non-classical theory, that this doesn't work. Similarly, somehow related probably to inconsistency of measurements. And there is second part to this observation. However, the classical picture always persists for the latest readout of the sequence. Say due to causality. So in other words, if I deploy my coarse-grained device here rather than mid-sequence. Omega Fn bar Fn. I actually get sum over Fn bar. Okay, so let's take a break right now, okay, and be back in 5 minutes, okay, just to have a breather. Okay. So if you guys have any questions, go ahead and ask. I will be patiently sitting here waiting.
Hi, Piotr.
Okay, good.
I have one small comment. I admire your way of making everything formal. To write it nicely in some nice symbols, I would never be able to do this. I would rather say that if I measure F1 and F2, and probability of getting F1 is P of F1 and measuring F2 is P of F2. So if I measure something which doesn't distinguish in classical mechanics the sum of this probability. But you are able to make it very sophisticated and nice in equations, mathematical equations. This formalism, when you go through it, is simple, but when you look for the first time and you see 10 definitions, 20 and 50 different symbols, and if you read it from the middle, is just no go.
It's scary,
but you do it very slowly, and I guess that this formalism is something that you have in your mind, and that's why it is that everything has been formally generalized to n, and so on.
Yeah, that's why I'm counting on interruptions for someone to, hey, what does it mean, and then I can
if it would be
words.
To me, I would say something. If I have result x1 or x2, and I have probability of getting this and this, and then I take device which measures sum of this x1 and x2. So in classical physics, this probability is the sum of this.
Yeah.
And here in classical mechanics is no, and this is called interference.
Well, we will get to that. You jumped ahead a bit, because yes, this is actually how you get to interference. This exactly where I'm going through. But this construction
I really admire the way of inventing these symbols and general formalism. It looks so sophisticated that
you know what it's.
But probably it is fruitful in some moment to have this format. Having only words is not helpful in more complicated situations.
I mean, it is kind of I think I will show in time why this was useful. Okay, it wasn't just waste of time, but if you look at so it looks really I'm really like tiptoeing, like on eggshells with this. I'm like explaining every single thing, mainly due to like historic reasons, because when we're developing all this stuff, we were like discussing with Łukasz and others, Fata, and other co-authors, and we are like discovering new ones on top of new ones on top of new ones. So this whole story is just it looks like this because it like incorporates all the objections we had along the way. So maybe it's like
and you work with mathematicians.
It's it's not, there's not much interesting math here really. But
it is the need for formalization.
yeah, this is kind of key because the discussions we had with guys, they were so they were like until we wrote down this kind of formulas, we weren't able to really like pinpoint what is bothering us, because
Okay, I understand.
so
Okay.
it's like
Yeah.
it's a only
Writing
after
them
we
down
wrote it down
precisely.
concretely. Yeah. We had to write it down concretely to even like identify what's going on, why there could be a problem, and to all this stuff. This is actually what led me to this discovery that
I understand. I
classical theories is
understand
only
that
unobservable.
then in order to abstract from the details, it's good to write it in some abstract form of some symbols.
Yeah. So it is kind of scary. It looks like maybe it's
Yeah, I agree
unnecessary.
that mathematics is simple. You are talking about probabilities and summing these probabilities and so on. In fact, you have two events, and you are talking about what if I have probability of the event A and event B. So the probability of that A and B will happen together is a sum, or it is not a sum.
Yeah. I mean,
Something like this.
This is essentially, this is essentially what it is. Yes. It's there's even people
And you say how strange quantum mechanics is, because when you think about classical mechanics, you always know when you have these fine probabilities, you can sum these probabilities and get some probability of some sum of the event. And this is not classical quantum mechanics, and this is experimental observation. So it makes quantum mechanics different.
Yes. So it's I appreciate that it's maybe too much yapping,
Okay.
but it's I think it's necessary to yap so much about this, because you have to be kind of careful with this stuff. Also,
Yeah, this is like teaching mathematical calculus. You have this general theorems, and then you don't even mention the numbers and real numbers. You have just theorem, but there are different ways of teaching it. You start from general theorem, and then you practice, take the function and find the derivative, or something. Uh, Sometimes it's good to give, and you are doing this. Some simple example. Now, this is the way, starting from something simple and then to generalize, and the other way is bottom up, or, or the other way around. You prefer something formal and then general, and then to give some naive example of two-slit interference.
Yeah, I mean, that would be the next step, because
You already gave
because
this example.
we are starting by
with
looking for counter
Gerlach.
example rather than example. Want to demonstrate that no example can be found, right?
Okay.
To show that it's, oh my God, there's difference here. This is different. This is not intuitive. What can we do now? And then I also try to like make it look sensible, that there is some story unfolding. That the clues are one clue leading to the other, even though in reality, when we are doing this stuff, the ordering was very different. There was like, historically it looked very different, and I just want to have a narrative that kind of looks like we are doing detective work here, where the one clue leads us to the other clue. And I don't know if it works. It's too much yapping for sure, but there will be some payoffs for doing this mathy stuff here. I mean, we don't have anything else than math at the moment, right? It's simple math.
No. I am not able, okay, yeah, sorry. I just wanted to say that I'm not sure if I will be able to be till the end, because I have some other duties soon. So just if I quit earlier, don't be offended.
Okay, no problem. Okay, so right, so we have our we have this observation. We know we are not even coarse graining. It does not behave as in classical theories, which is not super surprising, but at least we have some kind of idea what's going on. And now I want to make two more remarks. So jumping for a second to this cartoonish model of measurement, right? So if this kind of shows how coarse graining is achieved. So in this model, you just, if you make your wavelength of light longer, you are essentially being more coarse grained, right? Right, because more and more. So this is some wavelength lambda. So this is a wavelength lambda. If I go to some lambda prime bigger than lambda, right, I would have I mean, I'm sure you know where I'm going. This stuff. If lambda prime is even bigger than lambda, then the scattering will detect even more guys, right? There are more alternatives the device cannot distinguish between, right? So in principle, it's I guess it's possible to like manipulate the physical construction of a device so that you can adjust the resolution of the device, right? So you can think, okay, so what if I just push this idea to its extreme? What if I crank up lambda prime so much that it actually cannot resolve anything? Okay, so it's like extremely coarse-grained device. Okay, in principle, if I can adjust resolution, I can adjust it so much.
This is not device which doesn't measure anything.
Yeah, it should be like that, right? It's so bad at being measuring device that it actually cannot differentiate anything. Okay, so but it's still the measuring device because we just took one that worked and we just adjust the settings. So what would happen if I deploy this kind of extreme stupid device? What will happen? And you can, so we have another observation here, which talks exactly about that. Phenomenological observation number 4. I call it extreme quantum coarse graining. CG, quantum coarse graining will be CG. Okay. And let me write it down. Let F bar J device be an extremely coarse-grained and be an extreme CG variant of, move this window, of F device, FJ device, so that it is incapable of resolving solving between any alternatives. Or in other words, the resolution that we would ascribe to this device would be just single element omega f. So you have only one small omega, and the small omega is actually the whole, all the possible results of the fine-grained measurement. That's extreme coarse graining, where nothing is resolved. It's a stupid device, very dumb device. But then we can deploy it. Then deploying this device, deploying this device at any time in the sequence yields so yields the same result, as if no device was deployed at that time. So in formulas, P, and now we deploy our FJ, which is stupid device. And we do extreme coarse graining. So we have our alternative over all possible fine grain results. This is actually the same as not doing any measurement at time tj. So this is kind of like consistency for classical measurements, right? But it's not marginalization that gives us shorter. It's not marginalization that gives us shorter sequence, shorter probability, but rather you have to construct a device to do it, to achieve this kind of thing. Okay. So this is an input for sure for our deduction. And one more. We are almost done, I guess. But there is one more remark I want to make. Just again, kind of like a notation. Another remark about notation. So once you realize that you can have those coarse-grained devices that have adjustable resolutions, right? You want to adjust resolution. Basically, you want to be free to adjust resolution depending on what you want to achieve. So to make it more easier on us when doing the analysis of what we are doing, to essentially curb down the number of symbols we have to use. When I will be using F bar symbol, okay, rather than denoting some specific coarse-grained device with certain specific resolution, I will rather denote whole class of coarse-grained devices. Okay, so this class F bar will have all the devices that are some coarse-grained variant of the fine-grained F device. Each will have its own individual resolution. But I want to be able to rapidly inline switch between those different choices of resolution. So rather than specifying every time which particular device I'm talking about, I'm just talking about the class, and the relevant graining I will denote using will be defined using our V notation. So in other words, so when I write some P and there is F bar someplace, okay, so I'm saying, okay, I'm taking one of the coarse-grained devices from my class of coarse-grained devices, sometime TJ. And what is its resolution? Well, the resolution will be at least partially defined by the argument. So I have here omega fj, okay? So this does not specify completely the whole resolution of this particular device I have in mind at this point, because it essentially defines only one of the omegas, right? Usually there are more than one, but it will be sufficient for our purposes typically. And if I will need the whole, to specify the whole, the resolution completely, I would just say it explicitly, okay? So don't worry if at some point there will be F bar device on some left-hand side of the equality, and the right-hand side there will be also F bar device, but it will be the resolutions will be different on the left and the right-hand side. If there will be this kind of case, just remember I'm talking about a class of coarse-grained devices. The resolution, the relevant part of its resolution will always be indicated by the argument used in my probabilities. Okay, this is like this will come in handy soon. This kind of shorthand, another shorthand notation. So we could kind of finish here.